All right, let's get going then. You got it. Yeah, that's right. Now, so what I said I would do is that we'll record everything for this introduction to equilibrium, because what I'm going to do is I'll cover most of the key concepts in this lesson, and then I'll put it into this sector lesson. I'll attach it to sector lesson sometime over the weekend, because I've got nothing better to do. All right, anyway, chemical equilibrium. Let's have a look. So we talked about this last year, if you remember, when we introduced the topic of acids and bases, remember? And we talked about strong acids and weak acids, and we were starting to use this double-headed arrow, all right? And we had an option like that, where things were in what we would call probably total equilibrium, and then we used the idea of slightly larger and slightly smaller arrows to try and tell us where the equilibrium was predominantly situated. So obviously, if this is a reactant, this is product, reactant, product, reactant, product. This is telling me that in this instance, the equilibrium favours the products because the arrow is mainly to the right. In this one, this equilibrium favours the reactants because it's mainly to the left. So we spoke about that last year, and we said if it's all the way to the right, that means the reactants must be very reactive. That must have chemicals there that are very reactive, and we said it always goes away from the most reactive chemical. Now, that idea is not totally accurate, because we're going to introduce it now in the concept of the proper good equilibrium. Okay? So whenever we have reactants now in an equation, they obviously go towards products. We don't change the size of these arrows anymore at year 12. We now come up with a new equation, and the new equation, all right, called the general equilibrium constant, tells us how far to the right or how far to the left reaction is. We'll talk about what causes, or what conditions, I should say, we need in order to get equilibrium in a minute. So if I were to look at something like this, A moles of A plus B moles of B, this is the general equation that we use just to explain the concept. It goes to little mole, little c, C plus little d, D. This reaction, if I look at it now, has what we call a general equilibrium constant. When it's in equilibrium, I emphasise when it's reached equilibrium. Okay? And there are some things that we have to do with the system to allow it to reach equilibrium. It's not going to happen automatically. It's going to take some time to reach equilibrium. So the general equilibrium constant is the concentration of the products over the concentration of the reactants. We express it something like that, but when we use the real chemicals, it becomes the concentration of C to the power of C times the concentration of D, power of D, over the concentration of A raised to the A power and B to little b. So we now begin to write an expression that tells us something about what's happening in this equation once it's reached equilibrium. The actual value of Kc helps us to look at these things over here now. Alright? So when we begin to look at reactions that are in equilibrium, we can allocate a Kc value to them. Now, if you look in your book, and around about, where does this happen? Happen somewhere in the textbook. Yep, it's on page 188. And it's basically telling us what does a Kc value tell us in a reaction now. And it says if a Kc value is less than 0.1, it's fairly small. But what does that mean in terms of where the position of equilibrium mainly lies? Jack?
Low yield of products.
Good. So if we look at just this idea here, the concentration of products over concentration of reactants. So if this proportion, if this ratio is small, it fairly obviously means we've got not many products. Okay? So this reaction predominantly is like this. In other words, this reaction is telling me it's got a low Kc value, less than 0.1, we define that as being small, then it favours the reactants every single time. So that tells us something about the position of equilibrium. And I'll use that word many, many times over the next few weeks, because what we're going to do is we're going to move the position of equilibrium for one reason or another, normally towards products. So we do have a Kc value that's small like that, but if I want to produce lots of products, we're going to learn how I force the equilibrium to go to the right. So I change things like the temperature, I change concentration, I change pressure. Alright, so those things we talked about recently in relation to the rate of reaction, and we don't want to confuse rate with equilibrium. We'll talk about that in a minute. Kc equals 10. That's telling me that it's large. So the Kc value is large. So if I wanted to use that small arrow, large arrow, it's telling me that predominantly in this equilibrium reaction, that the products dominate. There's lots and lots of products in this instance. Okay? So the value of Kc tells me something about the proportion of products to reactants. But we don't use these different sized arrows anymore. Okay? They're now gone. We only do that here 11. We just do this and we use the Kc value, and then we talk about where the equilibrium position is lying. Everybody cool with that? Alright, now, I haven't said what we need for equilibrium to occur, and I haven't said what happens once equilibrium is reached. One thing I didn't mention was this. This will only happen at a constant temperature. The temperature that we normally work with is 25 degrees Celsius, okay, or if we add 273 to that for Kelvin, it is 298 degrees Kelvin. Okay, and we call that room temperature. So unless we're told otherwise, what we're saying is the Kc value for this reaction is this number at this temperature. If I change the temperature, the Kc value changes. I get a new Kc value at a different temperature. Everybody okay with that one? Now, so what we have then is a reaction that is in equilibrium. Okay, and a few things have to happen for a reaction to get to equilibrium. First thing is, if we're ever going to achieve equilibrium, then we talk about systems that are open and systems that are closed. An open system allows your reactants and your products to escape to the atmosphere. Here's an example of one. So if I, for example, was going to react together, let's say I've got sodium carbonate, and I'm going to react with that hydrochloric acid. I'm going to try and get that set up in an equilibrium system, in an equilibrium environment. If I do the reaction, it's going to be obviously carbonate plus acid is going to give me carbon dioxide plus a salt, which is probably going to be sodium chloride, plus water. So all I'm doing is I'm just creating bubbles, okay, and carbon dioxide is a gas that's escaped. Now, if I leave this system open to the atmosphere, what do you think is going to happen?
You lose products.
I'm going to lose products. So if I'm continuously losing the products from any reaction, are we ever going to reach equilibrium? No, because it's just going to keep on going to the products, to the products, to the products. Now we use that later on to force a reaction to products, because if we take the products away, remember the Kc value was a constant, so if I take products away, that gets smaller, so to keep Kc value constant, if I've got a constant temperature, the reactants get smaller. If I take more products away again, the reactants get smaller again. Hopefully you can find that, that's a logical sort of a conclusion. So if I'm taking products away from a reaction, it's going to keep on going towards products. Similarly, I could reverse it. If I could take the reactants away in any equilibrium situation, it's going to go back towards reactants and try and put those back again. But it can only happen in that instance if it's already at equilibrium. So in order for this to happen, we need to do this. We need to make it a closed system. So we can only get equilibrium happening if the system is closed. Now, I'll just reiterate that a little bit. Because we only need to think about a closed system in what scenario? What do you reckon? Jack? Gases, yeah. So we only really need to consider this if I'm using gases as either reactants, okay, or products. Outside of that, if we're working with solids, if I'm dissolving a solid, for example, into a liquid, we don't need to worry about that. Because, why not? Why don't we need to worry about solids or liquids? They're not going to disappear anywhere. We're not going to lose them, okay, at all in the system.
Hello, I'm looking for the audio amplifier.
I don't have an audio amplifier on me.
No, you borrowed one and you can't find it.
I borrowed it.
It did something with sound a while back. It looks like a cowpack. Yeah.
No idea. I didn't stash it. Okay, you're on my video away.
Sorry.
Okay, so back to this again. First thing is we need to get equilibrium is a closed system. It must be closed. Alright, if we have an open system, so we use that terminology, closed system, open system, it's going to be very difficult to reach equilibrium. Alright? Of course we could. Oh, the other thing is we have to look at what's going to happen once equilibrium is actually reached. A few things happen. So when we reach equilibrium, by the way, I use that symbol for equilibrium. You can't use that in the exam. Alright, it just helps me to save on text. Alright. So, once equilibrium is reached, can anybody tell me what happens with the system? Good, okay. So as soon as the equilibrium is reached, the first thing we have to remember is that the rate of the forward and backward reactions are the same. They don't change. Why does that have to be the case? Because the Kc value is constant, but if the rates were different, will we ever get to equilibrium? No. That means we'd always be getting more of reactant or more of product. We'd never get to a point of the actual equation being able to reach some sort of a balance. So as soon as we reach equilibrium, the rates of forward and backward would be the same. Let's just go back one step. 3 steps, all right? What do you think is going to happen when we mix the chemicals together initially? Jack, what do you reckon? Which will be the fastest rate, the forward reaction or the backward reaction? Forward, okay. So while equilibrium is being established, okay, the rate of forward reaction is going to be greater until it reaches equilibrium and the back reaction kicks in. Okay? And we had that yesterday, or whenever we talked about it. So if we were to look at this reaction, and if I were to just consider the concentration, let's just put it back on the board again. So if we looked at, say, sodium carbonate plus HCl, acid plus gives carbon dioxide plus NaCl plus H2O. So I could actually monitor that reaction. I could look at, say, the concentration of hydrochloric acid, and I could look at say the volume of CO2 if I wanted to, all right? So let's just keep it simple. I'll look at this and this as two chemicals, all right? One reactant and one product. So the sodium chloride starts off at 0 and it's going to go something like this, and eventually its concentration will remain unchanged if I'm using this as being a sodium chloride concentration. If I'm going to look at the hydrochloric acid concentration, as that's used up, that's going to do the same thing. It will continue down, and at the same point, it should also become a constant concentration. So, in terms of what's actually happening, remember the slope of this line is our rate, okay? And it looks like that the rate obviously is going to taper off, so initially it's very fast, then it's going to slow down, slow down, slow down, and it looks like the rate is 0, but it's not. It means that the reaction has reached equilibrium, because at this point, the concentrations remain constant. So we have to think about this as how we represent a reaction that's entering into equilibrium. So the concentration of the products, okay, obviously are going to be 0. That's going to increase over time. Concentration of reactants, all right, is going to be 0. Sorry, what did I say that? Concentration of products is going to be 0, and concentration of reactants is going to decrease over time as they produce the products. Okay. If we look at both of these numbers here, let's come back to this. Okay, who can tell me which of these equilibrium reactions occurred at the greatest rate? Careful, David. Which of those ones is going to have the greatest rate? Jack?
Be the one greater than 10.
One greater than 10. It's the most common question in the exam, and it's the most common question that people get wrong. So which one of these reactions, okay, will have the greatest rate? What do you reckon? So, Dave, what did you say? David said less than 0.1. Jack said the other, he did opposite. He said 10, greatest rate. Okay. Anyone else? Any other takers? So we've got two possible answers.
I mean, like what someone else said that we can take that they'd both be about equal.
What? So you're saying now both of those have got the same rate?
If you put it put 1 and 10, they would probably be about equal.
Okay. So we've got now 3 answers. Okay. So one person says no, the KC with 0.1 would have been the fastest rate. The KC with 10 would have been the fastest rate. And Jack says no, the same rate. This is the rate how fast the reaction would have been produced, yeah. What do we think? So people now think 10. What are you going for? You think 0.1? And now we've got 3.1, 2 at 10, 1 in the middle. What do you think? 10. Okay, I already know the answer. So, unfortunately, nobody's got the right answer yet. Alright. No one. Alright? Anyone else want to have a go?
No.
The answer is?
No.
Neither of these values tell us anything about the rate of reaction. None. None of them. This is the first thing that people misunderstand in relation to the KC and the whole concept of equilibrium. They see a large value of KC and they think, oh, that's a fast reaction. It's nothing to do with that. Alright? So all the KC value tells me is that when the reaction has reached equilibrium, in this instance I've got a lot more products than reactants. It doesn't tell me how fast it got there. It doesn't tell me how slow it got there at all. Okay? So that is most critical, that you understand the KC value, the magnitude of the KC value doesn't tell me anything about the rate of reaction at all. And that's the most obvious question, and it's the it's probably the question that most people tend to get wrong. Because the KC value doesn't tell us anything about the rate. All we know about the rate is that once the reaction has reached equilibrium, the rate of forward and backward reaction is the same. As Jack told us a minute ago, as the reaction proceeds to equilibrium, we would expect the rate of forward reaction to be faster than the rate of back reaction, because initially, based on your understanding of rate, the concentration of A and B initially is high, so you expect the rate of forward reaction to be great. And then as soon as we get some more C and D, then of course they become dominant and then they can reverse or react in the reverse direction. But it's pretty hard to get anything going back in that direction if I've got nothing there initially. Their concentrations are small. Everybody got the idea? Alright? Jack?
So the Kc value just tells us the amount of product and reactants.
That's it. All the Kc values tells us is the proportion of products to reactants, okay, once the Kc value is reached, once equilibrium is reached. Now we could come back and do this, by the way, alright? There's nothing stopping us from doing this. So I could add a catalyst to this reaction, or, in this instance, how would I make this reaction go faster? How would I make it reach equilibrium quicker?
Add more reactants.
How would I make this reaction get to equilibrium quicker?
Make more surface area.
Yeah, increase surface area. So I could use powdered sodium carbonate. Now if I've used the same mass of solid, I'd end up with the same concentration at equilibrium. It just gets there quicker. Okay? Or I could increase the concentration of the hydrochloric acid used. Okay? Increased concentration increases the rate. So that means this graph is simply going to get a little bit steeper, but it's still going to be, for the same concentrations, at the same temperature, the Kc value will be the same. Not going to change. Alright, back to this. At equilibrium, we know that the rate of forward and back reactions are the same. They have to be. Otherwise, we're never going to get to equilibrium. What else do we know happens at equilibrium? What else happens at equilibrium? Anything else happens at equilibrium? Sort of in here somewhere. Three things. Anything else? So the rates remain the same. Equilibrium's been reached. Has the reaction stopped? No. Okay. So although if I got rid of my flask, if we had the flask sitting on the bench and if I was doing sodium carbonate reacting with hydrochloric acid, I put the stopper in, the reaction would go vigorously, and all of a sudden it would slow right down. And the question is, has the reaction stopped? Will said no. Okay, because all I've done is I've allowed the CO2 in the atmosphere and the sodium carbonate and the acid to come to an equilibrium. I haven't let the carbon dioxide escape. Alright? So we need to highlight that the process is dynamic. Okay? In other words, it doesn't really stop. So the equilibrium is ongoing once we reach it. So although it doesn't look like it, once we reach equilibrium, the reaction is still active in the forward direction and it's still active in the reverse direction. But sitting from the outside, we don't see any change once equilibrium has been reached. Okay? So it is dynamic. So the rate's the same. The dynamic means it goes basically the same, that is, goes forward and backward, okay, all the time. The old textbook used to have a picture of a person walking up an escalator. And so, obviously, if you are trying to get to equilibrium, initially you go fairly fast up the escalator. But if you walk at the same rate as what the accelerator is going down, you've reached equilibrium. And so the escalator is still moving, you're still stepping, okay, but you don't see any change in your position. So think of when a reaction reaches equilibrium, if that helps, escalator going down, you walking up the escalator, okay, and if you don't keep pace with the rate, if the rates aren't the same, if you don't walk at the same rate going up as what the escalator goes down, you're going to go in one direction or the other. So to get equilibrium, you've got to maintain that rate in both directions. Whether you're going, it'd be difficult going down, but you have to step backwards, alright? Probably going up would be easier. David?
Would you say like a treadmill is
A treadmill, yeah. That's another example, because you're staying stationary, okay, but the treadmill is going in this direction, okay, and you're obviously forcing it with the legs in that direction. Right? So that's probably a good example of a reaction at equilibrium. Third thing is that the concentrations remain the same. We sort of said that already. Okay? So as soon as equilibrium is reached, the concentration of all the reactants and products do not change. They are fixed and they are locked in at constant temperature. Because if we change temperature, we get a new value of Kc. Alright, any questions in relation to that one? Let me do a quick check. So that's really your introduction to equilibrium, believe it or not. Okay? And everything in the first few pages up to 188 is in there. Alright, a couple of things in relation to Kc values. Okay, and it refers to this, concentrations. When we write out expressions for Kc, there are some things that we don't include in the expression for Kc. They are these. We don't include solids, and we don't include pure water. Any ideas? Well, we don't include these in expressions for Kc. Any ideas? Yeah, we can't change concentration. Let me give you a few examples of that. All right. Two examples of where we don't use solids and we don't use water. Here's an example. Sodium chloride solid plus AQ gives Na plus aqueous plus Cl minus aqueous. And we call that process, what do we call that? Remember? It's not what? No, I'm taking a salt and I'm dissolving it because the ions are already there. What's that called? Starts with an S, ends with an ation. Not salivation. Sation. No. Solvation. Okay, we're just dissolving the salt. That's all we're doing. Okay? So if we look at the expression for Kc for this, it's going to be the concentration of sodium ions times the concentration of chloride ions. Now, we would normally say this over the concentration of NaCl, all right, which is a solid. We don't include that in the expression for Kc. It actually does this. It becomes Kc times the concentration of sodium chloride. That's a constant, that's a constant. It's just a constant. Equals the Na plus concentration times the Cl minus concentration. So overall, we just do this. We say the Kc is equal to Na plus times Cl minus. That's it. So we drop the solid out of the equation. Okay? This is called the KSP. We don't use that term anymore though. The solubility product. Alright. While we're on this though, if the Kc value is really large, what does that tell you? If this Kc value is large,
More for us.
which tells me what about this solid? Very soluble or not very soluble? Very soluble. So the large Kc value tells me how soluble this salt might be. Alright, if the Kc value is small, it's obviously not very soluble in water. Here's another one. HCl plus H2O goes to H3O plus Cl minus. And I've seen that equation 1,000 times before. Alright, it is an acid-base reaction. So to work out this one, the Kc value is the concentration of hydronium chloride over the concentration of HCl, because this is pure water. And the concentration of pure water we worked out last year is what? Concentration of water in water, C equals N over V. We worked it out, it's about 55 molar. You can work it out. The number of moles in 1 litre of water. 1 litre, 1,000 grams, 18 divided by 1,000 divided by 1,000, okay? And it works out to be 55. Alright, so the Kc here, alright, for a ionisation, it's an ionisation reaction for an acid, you note doesn't have water in the expression. Okay? So we get rid of solids, we get rid of pure water. Not, if I had H2OG for gas, it's got to be in the equation. Why? It's, yeah, steam. So it could be more dense or less dense, the concentration could change. Alright, that's all we're going to do for our intro. Yeah, I'll give you back the test now, and then we'll have a chat about how people have gone with that.